All right, welcome. Today, we are diving deep into one of the trickiest but most important challenges in distributed systems, rollback recovery. We're going to talk about how these massive, interconnected services can literally turn back the clock when things go haywire. Let's get right into it.
So just picture this for a second. You've got this huge, sprawling service, maybe a global banking app or a massive online game with servers all over the world. Suddenly, one of those thousands of servers fails. How in the world do you hit undo for the entire system at once? How do you rewind everything to a stable, consistent state without just making a colossal mess?
Okay, so right about now, you might be thinking, hold on, what's the big deal? I've used database rollbacks. You just revert to a previous state, right? And yeah, that's a totally fair question. But trust me, in a distributed system, it is a whole different ballgame.
Well, it really all comes down to two absolute nightmare scenarios. These are caused by all the messages flying back and forth between different parts of the system. First, you've got a lost message. This is when a process sends a message, but the receiver rolls back to a point in time before it ever got it. The message is just gone. Poof, vanished. But even worse, way worse, is the orphan message. This thing is a true paradox. A process gets a message and does something because of it, but the sender rolls back to a state before it ever sent that message. So now your system's state is based on something that, according to its own history, never even happened.
So here's the bottom line. The entire goal of this whole song and dance is to find and restore what's called a consistent global state. And this isn't just any old collection of save points. No, it has to be a snapshot of a moment in time that the system could have actually been in, a state where no messages are lost and definitely no paradox-causing orphan messages are floating around. Okay, so that leads us to the next obvious question, right? If we need to restore the system to this perfect moment, how do we save that moment in the first place? What's the actual mechanism here? The challenge is pretty clear. How do we effectively press pause and create a reliable save point, not for one computer, but for the entire sprawling, complicated system? And the answer is a technique called checkpointing. Honestly, the best way to think about it is exactly like a save point in a video game. At a certain moment, every process takes a snapshot of its current state, all its memory, all its variables, the whole shebang, and writes it down to something permanent, like a hard drive. That way, if something goes wrong later, you can just reboot the system, and every single process can load up that last known good state and carry on.
Right, so checkpointing makes sense. We're taking snapshots, but this immediately brings up a huge design choice. Does every single part of the system need to take its snapshot at the exact same millisecond?
And this very question really gets to the heart of the two major strategies people use. The answer completely changes how you build your system, and it all depends on whether you force everyone to work together or you just let them do their own thing.
So you've got these two big approaches, and they could not be more different. Coordinated checkpointing, think of it like taking a group photo. A signal goes out, everyone say cheese, and every process freezes and saves its state at that exact same instant. You get one perfect, globally consistent snapshot. On the other hand, non-coordinated checkpointing is more like everyone taking individual selfies whenever they feel like it. It's way more flexible for sure, but trying to piece all those different selfies together into a coherent story later on, that is much, much harder.
And this is where you really see the trade-off. With the coordinated approach, that group photo, you are guaranteed to have a consistent state. It's perfect, but the price you pay for that perfection is high. Just getting everyone to synchronize takes time and resources. And, more importantly, if just one process fails, everybody has to roll back to that last group photo, even the perfectly healthy ones. It's kind of a blunt instrument.
The non-coordinated approach is pretty much the opposite. Here, only the processes that actually crashed have to roll back, which is way, way more efficient. But, and this is a big but, this brings back that huge problem we talked about earlier. How do you find a consistent global recovery line from all those independent selfies? How do you stop those orphan messages from being created? Well, to solve that, this approach needs an extra piece of equipment: message logging.
Okay, so that's the keyword right there, message logging. If all your processes are just taking checkpoints whenever they want, how on earth do you account for all the messages that are flying around in between those save points?
This is really the million-dollar question for non-coordinated recovery. We gained all this efficiency by only rolling back the parts that broke, but in doing so, we open the door to those nasty lost or orphan messages. So how do we solve that puzzle? The solution is message logging, and it's all built on this really key idea called piecewise determinism.
It's a fancy term, but the concept is simple. It assumes a process will always do the exact same thing unless something from the outside, like a message, changes its path. So if you just log every single message a process receives, you can bring it back from an old checkpoint and then just replay its message history to perfectly reconstruct its state right up to the point of failure. It's like having a perfect recording of its life.
But of course, it's not that simple. It turns out there are a few different ways to do this message logging. You can really break them down into 3 main flavors, and each one has some serious trade-offs. You've got pessimistic logging, which is the super safe one. It saves every message to disk before the process is even allowed to see it. It makes orphans impossible, but man is it slow. Then there's optimistic logging, which is the exact opposite. It's fast. It delivers the message right away and logs it in the background. But it's risky. You might have to do some complicated rollbacks if things go wrong. And finally, there's causal logging, which is this really complex compromise that tries to get the best of both worlds by tracking dependencies to only log what's absolutely necessary.
So we've gone through checkpointing, we've talked about coordinated versus non-coordinated strategies, and we've dug into message logging. Let's kind of zoom out and pull this all together to see what it means for actually building resilient systems in the real world.
At the end of the day, there's just no silver bullet here. A single best rollback strategy simply doesn't exist. It's all about trade-offs. Does your application need absolute ironclad consistency no matter what, even if it slows things down? Then a coordinated approach is probably your best bet. Do you need screaming fast performance, and you're okay with a slightly more complex recovery process? Then maybe an optimistic, non-coordinated approach is the way to go. It's that classic engineering balancing act between performance, complexity, and safety. And this really leaves us with a fascinating final question to chew on. In the real world of building and running these systems, is that theoretical perfection of a fully synchronized, perfectly consistent state always worth the performance hit? Or is it actually smarter to design a system that can recover quickly and efficiently, even if it's a little messy, as a more practical path to true resilience? Something to think about.
And that's all we've got for this explainer. If this helped you wrap your head around a tricky topic, do us a favor and hit that like button, share it, and subscribe for more deep dives. Thanks for watching, and we'll see you on the next one.